Good afternoon, everyone. My name is Raghu Balakrishnan, and for those of you who don't know me, I'm a professor and head of the School of ECE. Now, it's my pleasure to welcome you to this celebration of faculty careers colloquium. Typically, the introduction of the speaker is done by an associate dean or the dean from the dean's office, but occasionally the honor and the privilege falls upon somebody like me, and it's my good fortune that I have the pleasure of introducing Mike to you. Before I introduce Mike, I'd like to introduce the program to you. The Faculty of the Celebration of Faculty Careers comes out of our strategic plan initiatives, and part of it is something called the Faculty of 2020. And then the other component of it, which is aligning of the promotion and tenure policies with the goals of the college and things like, there are a couple, in simpler terms, here's how I see it. Most of us, we know Mike as a colleague, we see what he does, but, occasionally it's great for us to sort of sit and listen to his perspective of his career. So it's a great way for us to learn something about Mike. So that's goal number one. Secondly, I think it's good for all of us, senior faculty especially, to occasionally sit back and take an expansive view of where the career has been and plan a little bit for the future. So those are the two reasons why I think we have these colloquia. And again, it's my pleasure to introduce Mike. Well, just in terms of rounding off the project itself, the Celebration of Faculty Careers was piloted successfully in spring 2013, and with its full implementation of the 2013-14 academic year, so obviously it's continuing. And now it's my pleasure to introduce Mike to you. Mike got his BSW, MSW, and PhD, all degrees from Purdue. So he got his bachelor's and master's in 75 and 76. And then he went away and joined Intel Corporation, where he worked on the 8748, the first single chip microcomputer, and 8051, a second generation single chip microcomputer. And then he came back and got his PhD in 1981. And then he went away again. So you see the theme, and you see the connection here. So he went away again, and then joined the Central Research Labs at TI, Texas Instruments, as a member of the technical staff. At TI, his research interests centered on around gallium arsenide surface acoustic wave devices. Then in August 1984, he came back and joined the School of ECE as an assistant professor, associate, full, and now he's the associate head of ECE. He's a fellow of the American Physical Society, the Institute of Electrical and Electronics Engineers, IEEE, the Optical Society of America, the American Vacuum Society. But he's also received the 2008-2013 Motorola Excellence in Teaching Award in ECE, the 2009 and 2014 Wilfred Hesselbert Award for Teaching Excellence in ECE, the 2012 Tau Beta Pi's Dean Marion B. Scott Outstanding Professor Award, and the 2012 Murphy Outstanding Undergraduate Teacher Award. This is the highest teaching award given by Purdue University for undergraduate teaching. So he's won that. And then, funnily enough, then he won the College of Engineering's 2016 Potter Award for teaching. And obviously, the best teacher at Purdue. It doesn't make sense not to win the Potter Award, and you won that in 2016. So I look at, to finish off, he was also inducted in 2012 into the Purdue Teaching Academy, and in 2013 he was inducted into the Purdue Book of Great Teachers. So I think of Mike's career as being made up of two acts. The first act is when he was a stellar researcher. He's pretty much a fellow of every society you can think of. And then his second act is more recent, I think, and that is he has focused very much his attention on teaching. And in fact, I think of him as the conscience of teaching for ECE. As the associate head, he gets to interview every faculty candidate, and his opinion on teaching plays a big role in the decision we make as a department whether to make offers to faculty members or not. He is a great counselor for faculty members, especially junior faculty members, about how they can be better teachers. In short, he is the guardian of what we do in teaching. So I'm very pleased and privileged to have served with him as the head, and with him being the associate head. So we're going to learn a lot more about Mike, but please join me in welcoming him.
Thank you, Raghu. Well, the hardest part about putting this talk together was coming up with a title. And I had some that were a lot worse than that. Okay, just to give you a brief background. I was born in Hammond, Indiana, When I was about 6, we moved from East Chicago to Highland, Indiana. Graduated from Highland High School. My parents were young adults when the Great Depression hit, so the Great Depression and World War II had a big influence on them and hence a big influence on me. So I went to Purdue because it was in-state and inexpensive, and it was only 90 miles away. I got my BS and MS, and as Raghu mentioned, then I went and was a design engineer at Intel for a couple years, came back and got my PhD, left and was at TI for 3 years, and then kept coming back. So I came back for, I guess, the third and final time. Okay, so my father was in college when the Depression hit, so he had to drop out of school. He would have been the first college graduate in either side of my family. But from my oldest recollection, my family stressed education. And I can still recall, I was less than 6 years old because this was at the kitchen table in East Chicago, my grandmother talking to me about education and going to college. So I always, had that in the back of my mind. And my mom had 2 sisters, and each one of the sisters had a son who got a PhD. My 2 cousins were about 8 years older than me, so they did it first. One got a PhD in biochemistry from Wisconsin, and the other one a PhD in electrical engineering from Cornell. So when World War II came, my dad went into the Army, and he served in Europe. He was a prisoner of war in Germany for a while. In fact, when he was freed, his weight had dropped to under 100 pounds. So he had health issues for the rest of his life from that. And the Army did rule him as being disabled because of that. One nice thing about this program is I went and looked back at things, and I discovered, my dad didn't talk about it much, but I discovered, where he was held as a POW. So it was always, stressed about education and going to college, and one of my biggest worries was ever being able to financially afford it. But my dad being a disabled veteran, the state of Indiana had a program, well, they still have a program for children of disabled veterans, where there's a tuition and fee exemption. So when I came to Purdue, the tuition was $350 a semester. But for me, it was only $90 because of this program. So for 8 semesters, that's $720 what it cost me to go to Purdue. Now, when I originally applied, I applied to the School of Science and was going to go into physics because I had never heard of engineering or had no idea what engineering was about. But, after being accepted to Purdue, I looked into it more, and I actually switched to engineering before I actually showed up on campus, which was 3rd week in September, because back then the semester started about the 3rd week in September, and it actually ended in January. You'd go home at Christmas winter break, and then you'd come back for another week of classes and then final exams. So it was also fortunate that Purdue has everyone go into first-year engineering, because I had just learned what engineering was about. I thought I had learned what it was about, but I had no idea what discipline to go into. So it was useful to be in a first-year engineering program rather than picking a discipline. And one other thing, back then, I know they still had these courses, like we have a EE 190, but it was completely different back then. That was a 3-credit-hour course, and you really did things. You got into circuit design, power, so you really got a good flavor for the discipline. So I got my bachelor's in '75, and I didn't think I could do anything. How could I go to a company and really contribute? So I stayed for my master's. Uh, Also back then, they didn't have these summer intern programs. You know, during the summer, if you did something, you know, you worked at a restaurant, or for a couple summers I worked at the parks department, so I was cutting grass, lining baseball fields. A couple summers I worked for the street department, and that also entailed being on the back of a garbage truck sometime. So if I had any doubts about getting a college degree, that cured it. So there weren't these internships. So as I was working on my master's, Dave Stamm, who's one of our distinguished engineering alumni, was a fraternity brother of mine, and he was working at Intel. So I called him up and said, is there a chance I could come out there and work for the summer? And he said, well, let me talk to my boss. He called me back and said, sure, come on out. So I drove from West Lafayette to Santa Clara, California. And that's when I discovered it was really an interview. It wasn't an actual job. But I think it was a formality. So I talked to some engineers, talked to Dave's boss, Hank Bloom, talked to Hank Bloom's boss, Jean-Claude Cornet. And this is why I really know it was probably a formality, because even though I had a couple years of French in high school, Jean-Claude had this accent that when he interviewed me, I could understand only one word. And he said it a lot, though, microprocessor. So I just smiled and shook my head. And so I worked during the summer at Intel on the 8275, which was a CRT controller chip. And Danny Joa was the only engineer on that. And so what I was doing for him is the circuits were designed, and I had to run simulations to size all the transistors. And I must have done a good job, because when I left that summer, I had a job offer in hand. Okay, so back then, 2 engineers would work designing a microprocessor or microcomputer. The 8748 was the first microcomputer. And what that means is it had program memory and data memory on it. Okay, so it could, stand alone, run a gas pump, washing machine, microwave oven. And so here's a plot of it. So there's an EEPROM across the top here. Okay, so here's the EEPROM for your program memory. Here's the data memory and all the logic circuit. When this came out, it was the largest transistor at the time. Chip at the time. It was like 220 by 240 mils in diameter. Clear here because it was a PROM, and the way you erased it was with UV light. Okay, so the engineers who designed this were Dave Stamm and Dave Buddy. Okay, so I show up at Intel to start being a permanent employee, and Dave Stamm had moved on to a peripheral chip for the 8086 family, the 8089. Dave Buddy was from Oregon, and he wanted to go back. And Intel had just opened a place in Hillsboro, and he said, you either send me there now or I'm going somewhere else. So they were both gone. So here, I said half a year earlier, I felt like I couldn't do anything. I walk in the door, and about a week later, I'm in charge of the 8748, and it still was not a working, functioning chip. Okay, so it had gone through what we referred to as 3 stepping. So the A stepping, B, and C. So a stepping, you process the chip, it comes back, you test it, find out as much as you can about why it's not working, make the fixes, do another processing run. So we were down 3 runs like that, and things still weren't working. So my first job was getting that chip working. I'll just tell you one story. I remember one thing we fixed. The previous summer, when I started as my summer job, Bill Goodman started permanently. So he was fresh out of Kansas State. So by the time I went back 4 months later, he was a pretty seasoned engineer back then, Intel. He'd been there almost 7, 8 months. Okay. My boss, Gene Hill, was 30, and he was a real old timer. Okay. He was like Obi-Wan Kenobi. And that's appropriate because Star Wars came out while I was working at Intel. So anyway, Bill and I, we were good friends, and so one night we stayed up all night to try to figure out something that was wrong, because there were some instructions that this chip was supposed to run at like 4 megahertz, and once you got up past like 1 megahertz, things stopped functioning. So we stayed up one night, figured out which circuits were the problem, and that plot I was showing you, we had to go through, and by the end I knew what everything on there was. I could identify every transistor and why it was there. But you had these little jeweler loops, and you would look at the layout, and you could measure dimensions. And we found one transistor was drawn 2 microns, the channel was 2 microns too long. So fixing that fixed the problem. And I still remember it's the IB to port 2 lower signal. Okay, so after that happened, then moved on to the 8051. And this might have been the last chip at Intel where really 2 people did the whole thing. So I was co-designer with Steve Sample. Now that's not the Steve Sample who was an EE professor here and then was the president of University of Southern California. This was a different Steve Sample. But so each one of us had responsibility for about half the chip. So you would do the logic design, then you would do the circuit design, then you would simulate the circuits and size all the transistors. Then you would oversee, I forget what we called them. They weren't called draftspeople, but they were the people who would take your circuit designs and dimensions and draw all those lines and things you saw in that plot I had earlier. And then we had to oversee to make sure everything was being drawn right. So in the middle of that process, everything was designed except laying out the masks. I decided to come back and get a PhD. Okay, so I came back, and when I was doing my master's, I had TA'd this course 190, so I TA'd it again. And what I'd done at Intel was kind of a mixture of solid state and computer engineering. So I really didn't know which direction I wanted to go. But I took a course the first semester called Surface Acoustic Wave Devices that Bob Gunshore was teaching. And after the first exam, he had written "C" me on the exam. So thought I was in trouble. But he offered me a research assistantship. So that decided what I was going to do. I was going to work on surface acoustic wave devices. Okay, so these are devices like if you have a piezoelectric material and you put a transducer on, which is just like an interdigitated pattern, you can give it an electrical signal and launch an acoustic wave. And then you could convert that acoustic wave back to an electrical signal with another transducer. And one thing you can do is with the overlap of fingers and things, you can build in filtering mechanisms. And there were ideas for building convolvers and correlators with them. And Bob was looking at sputtering zinc oxide on silicon. So the zinc oxide would be the piezoelectric, so you could merge the acoustic wave device with the silicon electronic control. So that's what I did for my PhD. I didn't see too much future in those devices, so I didn't look for a faculty position at that time because I knew I would have to start probably in a new direction, and I didn't know if I could do that or didn't know how long that would take. And there's that tenure clock that's running. So I looked for a job, but the job market was really bad at that time. So I had 2 offers. One was from Intel, so I could go back and do the same thing I was doing. And I thought, well, I just spent 3 years in graduate school, and now I'm just going to go back and do the same thing. And the other offer was Texas Instruments, but I probably got that because it had to do with surface acoustic wave devices, an area I knew was probably didn't have that much of a future in it. So I took the TI job because TI was different back then. It was a big defense contractor. They had a central research lab, so I was going to work in the central research lab, and it was on a contract from DARPA for these gallium arsenide surface acoustic wave memory devices. So I did that. I knew that I was not going to be able to spend a whole career on surface acoustic wave devices. So I was sitting at my desk one day, and I got a call from Bob Gunsher, my advisor. And he said, Purdue has bought these 2 molecular beam epitaxy systems. I'm going to be using one to grow 2,6 materials. And there's a lot of faculty interested in gallium arsenide, and they want someone to collaborate who works on the materials side. And they knew the stuff you'd been doing with the sputtering of zinc oxide. So I came up for an interview, got the job, and been here ever since. Okay, so I joined in August of '84. Got through the ranks to full professor, served 2 years as assistant dean, and I went through 3 deans while I was assistant dean. So when I first started, Henry Yang was the dean, but after a while he left to be chancellor at UC Santa Barbara, where he is still the chancellor. He's been pretty successful there. Then John McLaughlin was interim dean for a while, and then Dick Schwartz became dean. And maybe because of all those transitions, I just had enough with administrative work. Okay, so I went back to being the best job at the university, being a full professor. Although later on, I got talked into being director of graduate admissions. Ragu's smiling. Ragu was associate head at that time, and talked me into being graduate admissions director. And then when he became an associate dean, he talked me into being associate head. And when I took on that position of associate head, I thought, well, I'll do it for at least 2 years, maybe 3 years. And as Roger Waters said, and then one day you find 10 years have got behind you.
No one told you when to run.
Okay, so let me talk a little bit about my time as a rank and as a professor here. These are just the collaborators I've had who had faculty positions at Purdue. None of the a lot of students and a lot of outside collaborators. In parentheses is the number of co-authored publications. So I've had an enormous amount of help from a lot of people here. Nice thing about Purdue, it's a very collaborative place throughout the university. So I've worked with people in the School of Science, electrical engineering, chemical engineering, all over. So the first MBE, I spent probably 75% of my time always fixing it. I was able to squeeze out enough good results that we were able to raise funding and then got a superb machine, this Varian Gen 2 molecular beam epitaxy machine. So this thing allows you to grow crystals of, like we were doing gallium arsenide, aluminum gallium arsenide materials, and have basically atomic layer control. I actually don't have many good pictures of it, but that's it. And right across the atrium here used to be my lab. Okay, so when I first got here, Mark Lundstrom and I were graduate students at the same time. He graduated about a year before I did and stayed on the faculty. So by the time I came back from TI, he was extremely well established, especially in the simulation of solar cells. So he had this idea about collaborating in an experimental project because for the simulations you need to know material parameters very well. So it was a program to measure things like minority carrier diffusivities, lifetimes, band gaps. And so he allowed me to be a co-PI on a contract we wrote and got funded by the Solar Energy Research Institute. So it was $600,000 for 3 years, and back then that was a huge contract. After 3 years, we got it renewed, but I learned because we only spent $504,000, we didn't get another $600,000. They just added $504,000 to what we had remaining. So we made sure we always spent it after that. Got renewed for 1 year in '88, then 2 years, then 3 years. And we were up for renewal in '94 and the Northridge earthquake hit. And that's when I learned when there's a site is called a national disaster where the money comes from. They tax existing agencies, and it was the turn for the Department of Energy to be taxed. So there was no money for renewal. So that's kind of what ended these studies. So let me just give you a flavor of some of them. So one of the things we wanted to get is like minority carrier diffusion coefficients and intrinsic carrier concentrations. Okay, and intrinsic carrier concentrations will vary with doping. So both these will vary with doping. So we were building homojunction transistors, and you don't really need gain from the transistor to measure the product of the minority carrier diffusion coefficient and the square of the effective intrinsic carrier concentration. So if you look at a Gummel plot, here's the base current and the collector current. So there's no gain. You know, the gain's like 10 to the minus 3 or something. But this is an ideal n equal 1 current for the collector current. So the only unknown is this product of the diffusion coefficient and Ni squared. And for a lot of simulations, that's all you need. But there are times when you'd want to know, say, the diffusion coefficient by itself. So we did, well, there's just results. So we plotted out Ni squared D versus doping for N and P-type material. To pull out the minority carrier diffusion length, we built a time of flight experiment. So we would hit a p-n junction with a femtosecond pulse and create a profile of minority carriers at the surface. And those profiles would diffuse to the junction and then get separated, and the voltage across the device would do something like this. So here's a plot. In the middle is a diffusion coefficient of 30, and the two lines are if you increase it or decrease it by 15%. So it's a pretty sensitive measure to getting that minority carrier diffusion coefficient. Okay, so then we did plot that out, measure that for P and N-type material as a function of doping. And then you could pull out the intrinsic carrier concentrations. And they vary because as you add doping, you're changing the crystal really, especially at high doping, so the band gap narrows. But you also, as the doping goes up, the material starts to be degenerate, so the Fermi level starts pushing towards and then into the bands, and you actually get effective band gap widening. Okay, and also, for people to believe these numbers, we had to show we were growing material comparable to what everyone was building solar cells with, which was a process called metal-organic chemical vapor deposition. And the world record was 24.8%, and the cell we made by molecular beam epitaxy was 23.8%. So it was near the state-of-the-art material. Okay, so let me talk about another collaboration. When I interviewed, first time I met Jim Cooper, and we really hit it off in the interview. And back then, people were thinking that we're going to make high-speed microprocessors out of gallium arsenide. So Jim was working on dynamic memory. And he was looking at storing charge at the aluminum gallium arsenide interface, which had like a 3/10 EV barrier. But I was working on these memory correlators that were using reverse bias PN junctions for storage in gallium arsenide. So we kind of put things together and started working on these gallium arsenide non-volatile or random access memories. And I'll tell you in a minute how that led to working on silicon carbide. But just briefly, it's very similar to silicon DRAM, except you're not using the semiconductor next to the oxide. You have a PNP with the middle N region floating. So if you put a negative bias on the left-hand side, you're forward biasing this junction, reverse biasing this one. So you're going to pull some carriers out of the floating region in between. So when this bias goes back to ground, you have a deficit of carriers, and the way you lose those is through thermal generation, which is a very slow process, especially in gallium arsenide with the 1.42 EV band gap. Okay, so we're working on this project on memories in gallium arsenide. We were having funding from the Strategic Defense Initiative Organization. So we were at a program review, and it was being run by our program monitor, which was Max Yoder from the Office of Naval Research. And Max is a Purdue grad from back in the 50s. Well, there was a group from Cree Research there also presenting their work, and they were working on silicon carbide. They were making these single crystal wafers that were maybe an inch in diameter of silicon carbide, but its band gap was over 3 electron volts. And Max goes, why don't we take Purdue's memory and make it in silicon carbide, and we'll have a non-volatile memory. So we struck up a collaboration with John Palmer and Kelvin Carter at Cree Research and started to shift from working on gallium arsenide to silicon carbide. And so the idea, you would have your storage cell, and then you would have electronics to access it. And the interesting thing about silicon carbide, you can do things the thought was you could do things very similar to silicon, because if you oxidize it, the carbon leaves as CO or CO2, and you're left behind with a thermally oxidized silicon carbide wafer. So we had to do a lot of work in process development, so we did a lot of, like they did in the early days of silicon, trying all sorts of different parameters and measuring surface state densities and finding the ideal things to where you could build an effective MOS technology in silicon carbide. We built that non-volatile memory with Cree, 64-bit one. We even built some CCDs. And you might say, why would we build a CCD? Well, remember, this was the Strategic Defense Initiative Office, and they wanted to find ICBMs as they were being fired. And one of the things that happens is the UV signature from an ICBM. So they wanted a solar blind photodetector. So silicon carbide with an over 3 EV band gap could look right into the sun and not really see it, but see the missile coming out of the sun. But we've finally moved on to things that were more practical in silicon carbide, and that's power electronics. So we built some high-power Schottky diodes. Here's one with could block voltages over 5,000 volts. We made some of the first silicon carbide DMOS power transistors. This first one could block 760 volts. UMOS, this one was about 1,500 volts. And although I haven't participated in this work for a while, it's still going on here at Purdue. So let me just talk briefly about something I worked on that was a lot of fun. I don't know if it ever did or ever will have any practical application, but it was a fun material science. So molecular beam epitaxy is basically a fancy thermal evaporator. So you have these cells that contain materials like gallium, aluminum, arsenic, and you heat them up and start evaporating material. And you have these shutters so you can turn the beam of atoms on and off abruptly. Here's the wafer you're going to be growing on, and typically the growth temperature of the wafer is about 600 degrees C. The gallium's sitting at about 900, and the arsenic sublimes at 280. So every gallium atom that hits the surface is going to stick. And an arsenic atom is going to stick only if there's a gallium atom to bond to. So you're almost guaranteed you're going to get stoichiometric material with growth conditions like this. So at Lincoln Labs, there was a break in a thermocouple or something, and the temperature of the substrate went way down, and they said, well, let's just ramp it back up and keep growing. And they got a good crystal doing that. So that seemed interesting, so I started to look at that. And so we grew some material where the growth temperature was down to like 200 degrees C. Do an X-ray, you get it's a good crystal. This is from the underlying substrate. This is from the epi layer we grew. And what this shows is you have a good crystal, and this spread is due to a strain in the crystal because of the excess arsenic that's all over inside. And you could tell from this split that we were getting about 1% excess arsenic. And then we took this material and annealed it, and most of the strain disappeared. Okay, so the arsenic was going somewhere. So Nobuo Otsuka, who was a professor here in materials engineering, was a great transmission electron microscopist, looked at it and found that all the arsenic was precipitating out. And that the longer you anneal the sample, the bigger and fewer the precipitates. It was an Oswald ripening process that was going on. So what we found is that we could grow any concentration and size of arsenic precipitates by a combination of growth temperatures and how much we annealed the samples. So this is one we grew where we had gallium arsenide, aluminum gallium arsenide, showing you'd get the precipitates everywhere. But when we looked at this, it seemed like, well, there's a lot more at the interface here, right on the gallium arsenide side. So we grew a structure where we had like 1% arsenic throughout, and then annealed it, and you saw precipitates forming everywhere, but they're starting to preferentially form in these 100 angstrom gallium arsenide regions. And the more you annealed, the more they would move. Okay, it was strictly that the gallium to arsenic bond is weaker than the aluminum to gallium arsenide, aluminum to arsenic bond. So it's a lower energy state if all the precipitates end up in the gallium arsenide. Another interesting thing was the effect of doping. So here's a structure where we had some beryllium doping just in these regions and silicon doping here. And you'd see that the arsenic precipitates preferentially go to where there's N-type doping and away from where they're P-type doping. So an arsenic precipitates forms a Schottky barrier in gallium arsenide. So if you're in an N-type region, it's going to be negatively charged. So if you think of an arsenic precipitate at annealed temperature getting emitted from the arsenic precipitate, it's going to be positively charged and coulombically attracted back. So that's why there's that preferential precipitating on the silicon regions. Okay, one thing I didn't have in that list of things was that in July of 1999, I had a startup company called Optolinks. And we were making high-speed photodetectors and photodetector arrays for datacom and telecom. So when's the worst time to get into the datacom and telecom business? It's right before February of 2000 when the internet bubble burst. Okay, so we didn't make it, but I ran across this quote that's really accurate, and I think it's accurate for any startup. You are never closer to your greatest failure when you are at the moment of your greatest success. Okay, and there were at least 3 times with Optilinks where that happened. I knew someone well from conferences who was on the investment board at TRW. And TRW back then was investing in companies and giving them technology because they found it more profitable to have stock in a startup than make the product themselves. Then they could sell that stock for a lot more than they would get from the products. And we had a term sheet from TRW. And I happened to be on vacation in Wyoming when that happened, and back then cell service wasn't so good at places. And one of our investors here sent a, can't think of the word, he tried to negotiate the terms and sent them a revised, term sheet. And, the way TRW viewed it, we could say yes or no, and that was saying no. So that was the end. And when I talked to my friend, he said, the board was sitting there going, who do these guys think they are? And that's, how I kind of felt. Oh well, so that didn't work. So then we got a working with Cypress Semiconductor because Cypress was getting into the datacom modules. And one of the things they told us was that if they were going to use our parts, they would only do that if they would buy us. And after the dot-com thing was imploding and we lost the deal with TRW, it was like, yes, you can buy us. Then we got a call from them saying, well, Cypress is getting out of the datacom business. We're never really getting into it, and we're all looking for jobs. So that ended that. Then there was a third chance. Molex ordered $80,000 worth of our photodetectors to qualify in their datacom modules. That's when I learned that a purchase order isn't a contract, especially if you're a small company that can't afford lawyers, maybe. They took delivery on only $20,000 worth of it and never any more. And at one point, when they placed that order, they said, well, we're going to be needing $250,000 a month of these, which would have been enough to really, sustain us. Okay, so that was the end of Optilinks. So I had to, I had former students of mine, other Purdue students were in the company, so I kind of felt real responsible, and I kind of let my whole research program here kind of dwindle. In fact, when I came back, I had one graduate student left who was just about to finish. So at that time, Mark Lundstrom and Supriyo Datta had 2 large centers starting that had big education and engagement programs in them. And the faculty member who was going to run that had just decided to leave Purdue. So they asked me, would I be the director of that? And I thought, well, yeah, that'd give me a time to kind of figure out what direction do I want to go. So I started to do that. And let me, for time's sake, we had a lot of programs like summer research interns. But let me just talk about one of them that I did with Ron Reifenberger, faculty member in physics. We were working on a nanotechnology museum exhibit. And we did it under the EPICS program. And so things we did were, it was going to have a Lego model of how an atomic force microscope worked. There would be kiosks with animations and hands-on activities. And then it was eventually displayed at the Children's Museum in Oak Ridge, Tennessee. And now a lot of the parts are over in the atrium of the Burke building. So that was just the flyer for it that was distributed in Oak Ridge. There's a picture of it in Oak Ridge. So this is our cantilever arm, and here's the Lego landscape. I'll show you how it works here. Just like in atomic force microscopes, you have a Lego landscape, the thing comes down, and there's a mirror here that gets deflected when the surface hits. So there's a laser beam reflecting off this, and when it gets bent, it no longer hits a photodetector on that column, so you know when you've touched. so you know the height of where you touched. So you can go through and scan the whole surface just like an AFM does, and there you can see the laser beam being deflected. And there are some of the kiosks with the animations, the children playing with some of the hands-on activities. And we had a camera up in the corner of the room so we could watch, took a photograph like every 30 seconds, and then when school groups came and visited, we could get nice pictures of it. And Ron had a lot of nice AFM pictures that we made and had them framed, and you see a lot of those over in Burke now. And once we moved it to Burke, for a while we used to have a lot of summer groups come through for tours. Okay, so I mentioned how I became associate head. And one of the tasks of being associate head is making all the teaching assignments. And as associate head, I have complete release from teaching. But what I found early on is it's really tough to make all these teaching assignments, and when I would get down to the very end to get it over with, I'd assign myself to a class. But I like teaching, so that's fine. So one of the courses back 10 years ago I occasionally had trouble staffing was 311 electromagnetic fields. And I had taught it a couple times before, but not often. And so I started to teach it more regularly. And the students were always saying at the beginning, God, I dread taking this class. They put it off to the last minute, like it's a junior level course, but they take it their senior year because they need it for senior design the next semester. I was thinking, this is the greatest material. I mean, it's fundamental to all aspects of electrical engineering. You can understand how many things operate, so motors, railguns, spectrometers, braking, transformers, batteries. So I started to make little demonstrations because I thought they can picture these things, then they can develop mental models, because I think they were all approaching this and learning it as some abstract math. They weren't developing mental models of these things. Because if you have the right mental model, you don't have to remember Maxwell's equations. Like Gauss's law, you just think a charge, flux coming off, closed surface, all that flux goes through it, you can count it, that's equal to the charge inside. You got Gauss's law. You can do that with all these equations. This is one course where you can understand everything from the very beginning. So I started to make these little demonstrations, and then I actually started to video them so I could put them up on Blackboard too. And I then started to make additional videos. I would make short ones explaining concepts, and I probably have about 50 of these 2 to 10 minute videos that I use when I teach that I put up on Blackboard. And let me give you some examples. So this is an electrostatic motor, one of the first motors in the 1700s that were looked at. So basically, you have some aluminum strips, you put a high voltage on this end and ground this end. So what happens is you pull electrons off air molecules and they get repelled, deposited on the aluminum, positive to positive, it rotates. And then they get, you have a positive then on this side that pulls electrons off this one. And these things really have a lot of renewed interest now for microelectromechanical systems. A lot of motors and micro machines, silicon, are being built on these concepts. And there. Okay, so I connect up the high voltage and it should start spinning. Okay, so that's an easy demonstration that you can actually teach a lot of things with. Okay, we'll come to another one here in a second. If you recall Faraday's first motor, it's very similar in structure to this one. So this is a clear way of seeing that IDL cross B. You have a magnet here, current flowing through the wire, so magnetic field lines like this, IDL cross B. You get a rotary motor out of it. So that's very similar to the one Faraday did, except he had his wires sticking in mercury. Here's a linear motor. So this is a bare copper wire. So the battery has two magnets, and where the magnets touch, then you have a current flowing. So there's just a current flowing where the magnet is. And so this causes a magnetic field down the center of the coil that pushes on the magnets. How a battery works, or how static electricity works. So you put two materials together. They have different electrochemical potentials. So there's going to be a transfer of charge until the electrochemical potential goes to zero. Okay, a lot of people think, well, this friction rubs these electrons off. It's not that at all. It's the difference in electrochemical potential. The rubbing just enhances a lot of contact. But after the charge moves, it stops. So the way you sustain that electrochemical potential difference and make a battery is you put a solution between it, like salt water. So that's a salt water soaked piece of cardboard. And so the salt water pulls the charge off so that you can sustain the current flowing. So you get a voltage. Okay, and then you can take these and stack them just like Volta did and keep adding up the voltages. So then you connect some wires and a light emitting diode, and you have a battery. And so I'll have that running all during class. Okay, so then you talk about, you have a current going around in a loop. That's a magnetic dipole moment. Fingers of your right hand in the direction of current flow, thumb in the direction of the magnetic dipole moment. You put that in a magnetic field, it's going to rotate till your thumb points in the direction of the magnetic field. Now in an actual magnet, you would switch motor, you'd switch the direction of current to sustain the rotation. This one doesn't have a commutator, so what I've done is I haven't taken the insulation off one side. So when M points in the direction of B, M disappears because the current's gone, momentum carries it around, so it'll keep rotating. Okay. Okay, so then you get to Faraday's law. Actually, I won't show the experiment, but you could do all the experiments of Faraday's law and show, the terms in the equation. It's pretty simple and straightforward. But then I also show how you utilize that to build an AC generator. So I have a water bottle that I have one continuous wire around, attached to a light-emitting diode. There's a magnet attached to this stick. So you turn the magnet, you're changing the magnetic field inside the coil. And the faster you turn it, the greater the change in magnetic flux, the greater the voltage that's going to be generated. So start turning it here. Get it turning fast enough, you get enough voltage for this to finally light, and it turns on and off with the frequency of the rotation. Okay, and one last one. So you talk about currents generating magnetic field. So if you have a coil, we've already gone over in class how that looks very much like a bar magnet. Okay, so then I have a coil on the bottom here. Okay, so I'm feeding the audio output from this CD player, which the students don't know what a CD player is. And so as that varies, the magnetic strength of this coil is going to vary. And I have a Okay, so I have a magnet here then that I'll hold close to this coil. And so there's going to be an attraction between this coil so I had to use Led Zeppelin, so there was a lot of sound so they could hear it in the classroom. Okay, I want to tell you about something else I did in class. Started this exam point recovery. Okay, so the idea is if the students attend at least 80% of the classes, they have this opportunity after each exam to recover lost points on one problem. So on that problem, they come and they have 15 minutes not to rework the problem or a similar problem, but to teach me the concept behind it. So they really have to learn it a lot better than they would have had to known to do it on the exam. Reason I did this was, first, I like to have a full class. I think I teach better when most of the students are there. And I hope if they're coming, they're bound to learn something. And let me mention some of the benefits. And a lot of these are ones students have told me. They said, well, it clearly leads to increased class attendance because I can observe that one. And it's an active learning by teaching because they have to come and teach me the concept. But some students have told me it really reduces exam anxiety because if they get to a problem they can't do, they said usually that just ruins the whole exam for them. But now they can say, I can spend all my time on the other problems. I can get these points back. I can figure out this concept and get the points back. And I usually have about 10 problems, so I don't think it stops students from studying because it's not a lot to recover, but it's enough that they're going to come to class to have this opportunity. Okay, we think of exams as assessment, but an exam is actually one of the best learning activities that we do. And there's many aspects of that, but I don't have time to go into it, but that's just one. Students become comfortable presenting a technical topic. So some of them are pretty nervous when they first come in and sit at a table with me and start talking. But it's better that they're nervous then than when they're on a job interview. And by the end, they're pretty good. And sometimes there's a student who I could tell from what they put on the exam, they were totally clueless. But they come in, they're an expert on the topic. So it's a human thing. Losses hurt. We're more sensitive to losses than gains by about a factor of 2. That's prospect theory. And so they'll put a lot more time in studying to get 10 points back than they would to earn that 10 points in the first place. Some of them start coming to my office hours then. I guess it was enough incentive to get them in. Now they feel comfortable. And if a student is really totally lost, I can help them at the beginning of the semester rather than just fail them at the end. And as I said, this is forcing them to learn concepts and not mathematical abstractions. And also the faculty or the students feel there's a faculty member who really cares about them. Okay, the first time I did it, I didn't think I'd do it again because of the cost. With 55 students, 3 exams, 15 minutes each, I spent about 40 hours that first semester doing this. But I thought the results were so good that I kept doing it. But it could probably be something you could incorporate and have your TA do. Just to give you some idea, these are the times recently I taught 311 before I incorporated this exam point recovery. The GPAs used to be about 2.7. Now they're around 3.1, 3.2. Even though there's really the number of points being recovered on average isn't really that much. Sad thing is it really hasn't helped this category because there's always a few students who just, no matter what, they won't come to class. And I think the students really enjoy 311 now. You know, they tell me that. And there's something that started happening a few years ago at the end of the class.
So I guess that's it for the semester. I really enjoyed the semester. I always like teaching this material, and I hope you enjoyed it and learned a lot too. And I'll see you next week during office hours and at the final. Thank you.
Okay, so I'm already over time, I think, so I think I'll stop here and see if anyone has any questions. Thank you.
All right, questions?
Where did you get your experiments from?
I just, thought of some of them. Some of them you can find concepts close to them on the, on the web, but I really wanted to not point them to things and build them myself, because one thing I found that, most of the time I put something together, it wouldn't work. So I actually learned a lot by doing it, and so something I can stress to the students, that you really don't learn things until you actually try to do them.
Well, let's thank Mike again.